I have you loud and clear.
Hello.
Welcome. Science.
And that is to say,
Physics,
medicine,
nature,
or
Space. Time.
the brain.
Life. The universe.
Hello! This week we're dipping our toes into water. Where does it come from? Could we ever run out? And I take a stroll through a local sewage plant.
Plus, in the news, on the hunt for malaria's Achilles heel, why coral reefs are being silenced, and a microscopic laser which could work inside the human eye. I'm Georgia Mills.
And I'm Izzy Clark, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First up, a new weapon in the fight against malaria. The disease, which kills over 500,000 people every year, is caused by a parasite transmitted by mosquitoes. The parasite is becoming resistant to our current treatments, so scientists are in a race against the clock to come up with new ones. And new research from the Wellcome Sanger Institute may help, because they've identified which genes inside the parasite's DNA are vital to its growth, meaning we can design drugs more effectively. Katie Haler heard more from one of the researchers, Julian Rayner.
There is currently a treatment for malaria, but one of the central problems with malaria is that the parasites rapidly develop drug resistance. So the current frontline treatment, which is a drug called artemisinin, is currently failing in some areas of Southeast Asia because the parasites have developed resistant to that drug. So there's always a need to develop new drugs to replace the drugs that we lose.
So this brings us on to your recent work. What did you set out to do?
Well, we set out to try and understand gene function in the most deadly human malaria parasite, Plasmodium falciparum. So what we tried to do is essentially mutate every gene in the parasite genome and see which ones were essential for the parasite to live and grow inside red blood cells and which ones the parasites could do without, were redundant.
And how did you separate these genes?
So we used an approach called transposon mutagenesis. What that means is that we inserted a small fragment of DNA called a transposon at random throughout the genome of the parasite, and then developed and used a system to try and identify where those insertions had occurred. So over a long time, this took many months, we generated more than 30,000 different insertions randomly throughout the genome, and then we identified where those insertions were. And what we saw is that some genes had several insertions. The transposon had gone in multiple times in different parasites, whereas some genes had no insertions whatsoever. And what that tells us is that the genes that had the transposon insertions, those insertions essentially disrupt that gene, they make it non-functional, and the parasite could still grow. So those must be genes that are redundant. Whereas the other genes, where we never saw any insertions, even though we counted more than 30,000 insertions, we never saw insertion in a significant number of genes, those are genes that the parasite must need to grow and multiply inside the red blood cell.
Oh, I see. And it's those essential genes that would make sense to target then?
Absolutely. So if you wanted to develop a drug against the malaria parasite, you need to target a gene that the parasite needs to grow. And this was the first time in the human parasite, Plasmodium falciparum, that we were able to essentially generate a full list of all of the genes that are essential for the malaria parasite to live. What we've done is essentially created a shorter list of genes that drug development can be targeted against, hopefully saving time, hopefully saving money, and also hopefully saving lives.
Would you be able to clarify where these potential targets would come into the life cycle of this condition, as it were?
So the malaria parasite life cycle is quite complex. It gets passed between mosquitoes and humans and back again. Within us, it first infects our liver and then comes out of our liver into our red blood cells. All the symptoms and all the pathology of the disease happen when the malaria parasites are inside our red blood cells. That's what makes us sick. And that's also where almost all drugs work. They kill the parasites when they're in the red blood cells, and that's why they cure you. The stage of the parasite that we were working on was the red blood cell stage. So we were growing the parasites in our lab, feeding them red blood cells, and mutating them with this approach to try and find essential genes. So this gene list that we've developed says which genes are important for the red blood cell stage, there are very interesting next steps to then take the same approach and apply it to other stages, because there are various reasons why you might want to target the malaria parasite either in the liver or even in some cases in the mosquito to try and block transmission from one person to another. There aren't good drugs that do that at the moment, and we're excited by the opportunity to take our approach and apply it to these other stages of the life cycle.
Julian Rayner from the Wellcome Sanger Institute in Cambridge there, and that work is out in the journal Science.
Now, from trying to take down a species to trying to save them. Coral reefs are the most biodiverse ecosystems in the oceans. They make up less than 1% of areas but host a quarter of all life. This makes for a noisy atmosphere. This is what it sounds like. Except that was from 5 years ago. This is how it sounds now. A group from the University of Exeter has been listening to the life beat of the Great Barrier Reef and found that it's about a quarter of the volume that it used to be. And this is going to have a devastating knock-on effect. Georgia Mills got the story from first author Tim Gordon.
Reefs are really noisy places. They're full of shrimps clicking their claws and fish chatting and chirping and whooping, and those sounds are used for all sorts of different things. Fish alarm call to warn each other about predators, they communicate with each other, they hunt together using sound. But what we've seen recently is that where we work on the Great Barrier Reef has been decimated by climate change. Tropical cyclones are happening more frequently and more strongly, and coral bleaching is wiping out whole areas of the ecosystem. And so when we went back recently and listened again to some of the areas that we worked in 5 years ago, it broke our heart. What used to be a raucous symphony of noise from this whole orchestra of animals is being silenced.
Oh, wow. And what kind of impact is this going to have?
It's really sad in and of itself to hear that degradation, but it's more than that actually, because the sound of a reef is really important for attracting fish to it. You see, fish start their lives as larvae out in the open ocean, where they're avoiding predators and eating plankton. And then once they've developed into juvenile fish, they then hear their way back home again. They come and find a reef to settle on, and they listen out from miles away in the open ocean to hear that reef. Now, we did an experiment where we showed that the sound of reefs today, that new, quieter, degraded sound, is much less attractive to juvenile fish, and fewer fish are able to hear their way home to it.
How did you test that?
So what we did is we built a lot of experimental replica reefs all around a bay, and on some of the reefs we put loudspeakers playing the sound of healthy reefs from 5 years ago, and on some of the reefs we put loudspeakers playing the sound of today's degraded reefs. And what we found was that on the reefs that played today's degraded sounds, we got 40% fewer fish settling to those reefs than the ones playing the sound of a healthy reef.
Right, so this is really making a big difference then in how many fish are coming back. What kind of a knock-on effect would that have on the reef?
It's worrying because reefs really need their fish, or the whole system starts to collapse. You see, fish help with nutrient cycling, they keep food webs in balance, they form associations with anemones, but most importantly, they graze away this harmful macroalgae that tends to grow over degraded reefs. This stuff's like sort of slimy seaweed, and when corals die, it grows over the top of the whole thing and chokes the reef. It stops any new corals from settling, any new corals from growing back, and it really slows down recovery. If there are fish on reefs, they eat away that algae. That clears bare patches and allows coral to grow back again. But if reefs don't have healthy fish populations, they're really stuck on what we call this slippery slope to slime.
Is there anything that we can do about this?
Absolutely. I think it is crucial that we remember that there is still hope. There's renewable energy technologies that are advancing all the time, and emissions are falling as a result. So in the UK, we recently broke our record for the longest run without using coal power in the UK. Our government's discussing plans to go carbon zero by 2050. So there is already progress in reducing our emissions. I think it just needs to happen faster.
Right, and while we're waiting, can we use your experiment method to lure fish back in while we wait?
Oh, this definitely raises that possibility, and that is research that we're actively doing at the moment. There's the possibility that we might be able to use sound to help with reef restoration, in that if we can, attract fish in using loudspeakers, it might help reefs to rebound quicker. But like we say, the most pressing issue really is reducing emissions, because any restoration efforts that we can produce will only be feasible on small scales and will only partially help to restore reefs. So if we're really serious about protecting what is the most beautiful and most valuable ecosystem in the world, then we really need to start addressing our emissions more seriously.
Let's hope we can save the rest of our reefs then. That was Tim Gordon from the University of Exeter, and that paper is out now in the journal PNAS.
And from coral reefs to your local duck pond, it's time for this week's Mythconception. Over to you, Izzy.
While the weather might seem in two minds about it, spring has officially sprung and brought with it the little quacking of baby ducks. So, it's an excellent time to go and partake in the most wholesome of Sunday activities. Going to the duck pond with a stale baguette to feed the birds. Except, it turns out that feeding birds with bread is a matter of loaf and death. But why is bread so bad when the ducks themselves seem to love it? Firstly, it makes them fat. And while a fat duck is an adorable concept, this makes it harder for them to fly or to avoid predators. And secondly, they get malnutrition. Bread is an excellent source of carbohydrates and not much else. So a bird that gorges itself on bread will fill up but still misses out on important nutrients. It's like the duck equivalent of junk food. The lack of a proper balanced diet can also be passed on to ducklings who won't develop properly in the egg and have laterally pointing wings and therefore unable to fly. This incurable condition is called angel wing. It can also lead to other diseases. The easy food supply leads to lots of ducks, geese and swans converging on the same point, and so bird diseases can spread more easily. Mouldy bread can also cause aspergillosis in ducks, a lung infection which is fatal. And it doesn't just hurt ducks. Uneaten bread in water is a pollutant, attracting pests and harbouring bacteria and mould. It can lead to a surface algae growth. Algae gives off toxins which can harm fish and frog life in the water and block sunlight from reaching the underwater plants, which can in turn damage the entire ecosystem. So, the bad news is, we wrought untold ecological damage as 6-year-olds. But the good news, if you still want to feed the ducks, then you can. The Canal and River Trust recommends oats, corn or defrosted frozen peas as healthy alternatives to bread, and also to try and find a feeding spot off the beaten track so no birds get overfed. So, the wholesome fun can continue, just without the whole wheat.
And if you've heard any suspicious sounding science, do drop us a line at chris@thenakedscientist.com.
From baffling British weather
sideways spines of the vertebrae coming off here
to looking at a cheetah from the inside out, games making their way to the clinic, and what to eat in your garden. The Naked Scientists In Short podcasts bring you a top-up of short, compelling science stories. Listen and download for free at nakedscientist.com/short or subscribe to Naked Specials wherever you get your podcasts.
Still to come on The Naked Scientists, a new microscopic laser could prevent counterfeiting, and I take a trip to a local sewage plant. The things I do for science. But first, last week Avengers Infinity War hit cinemas, breaking all the records for a superhero movie and taking over 29.4 million in its opening weekend. So, of course, Georgia Mills has taken the opportunity to brush up on some maths.
Have you ever asked someone under the age of 10 what they think the biggest number in the world is? The results are invariably amazing.
1,001,103,129,083. 90. 8 million? 7.
7?
Yeah.
That's quite a big number, isn't it?
Yeah.
Thank you to Emma, Claire, Sarah and Jim for sending those in. And to be fair to those kids, it's kind of a trick question.
There is no biggest number in the world, because if there were, we could always add one and it would be
bigger. So you might think that maybe the biggest number in the world is infinity.
This is Eugenia Cheng. She's scientist in residence at the School of the Art Institute in Chicago and also the author of Beyond Infinity.
Infinity is very large, but actually you don't have to be that dumb not to understand it, because it's very difficult to understand. And although it's something that you can think about even when you're a small child and you are having those arguments about who's more right, I'm infinity times right, actually it took mathematicians thousands of years to pin down what infinity is in a way that actually stands up to logic. So one way you can describe infinity is you can simply say it is the quantity of whole numbers that exist. And you might think that's cheating because you haven't said what it is, but mathematicians kind of like cheating. And then there's this funny thing you can do where you can actually make a bigger infinity. And so if someone says to you, oh, I'm right times infinity, then you can beat them. Not that everything is about beating people. You can say, I'm right times 2 to the power of infinity. And that's actually bigger.
But isn't infinity already the biggest number? How can there be a bigger one?
That's a good question. And the thing is that if you use the fact that infinity is the absolutely biggest thing, and then you work with it logically in mathematics, you very quickly find you can prove that everything equals 0, which is a bit of a problem. Because if everything equals 0, then there isn't really anything in the world. And that's okay in mathematics. You're in the 0 world. But it's not a very interesting world to be inside. But of course, there are other worlds in which everything doesn't equal 0, and that's why we actually need higher and higher orders of infinity to avoid everything collapsing to 0.
Infinity simply refuses to behave itself. Everything goes a little bit weird when you think about it. And a famous example of this involves an infinite hotel.
Oh yes, the Hilbert Hotel is one of the famous thought experiments involving infinity. So Hilbert's Hotel is an infinite hotel, and the idea is that there is a room for every number 1, 2, 3, 4, 5, 6, and so on. And suppose your hotel is full and you're the manager of the hotel and a new guest arrives. So you could either turn the guest away and say, bye, no room at the hotel. Or you could go, but I could make some more money if I move everyone up one room. So the person in room 1 goes to room 2. The person in room 2 goes to room 3, person in room 3 goes to room 4, and so on. And there's an infinite number of rooms. So you never run out of rooms. But now the room 1 is empty. So the new guest can move into room 1. So miraculously, the hotel was full, and now there's a spare room. And this is something you can't do in a normal hotel. In a finite hotel, if it's full, it's just full. But infinity is weird like that. And this is sometimes called a paradox, but there's nothing wrong with it. So it's the type of paradox which doesn't involve an actual fallacy. It just contradicts our intuition about the world. And that's not wrong. It's just we've discovered something. And so sometimes when we're thinking about infinity, the idea isn't exactly to understand infinity better, but it's to shed light on our actual world. So we also learn a lot about numbers that do come up in life by imagining what would happen if infinite things were true.
So this is quite mind-blowing, this idea, the whole idea. And I suppose we've evolved to live in a finite our experience of the world is finite. I only have 10 cakes or whatever. I'm never going to have infinity.
Oh, you.
Yes, it's a real shame. I'll never have infinite cakes. So I suppose it's not surprising that, well, to me at least, the whole idea is a bit like...
I think that's right. But the funny thing is that although we don't have infinite cakes, we do sort of have infinite pieces of cake. Because if you cut your piece of cake in half and then you take half of the rest and half of the rest and half of the rest and so on, that's what small children do to make their cake last forever, or at least that's what I did.
So infinity is useful for me to decide that my cake is going to last forever. But is it a useful concept in mathematics? Does it have any applications?
It's the study of infinity that led to the whole field of calculus. And calculus is really, it's all about things that continuously change, and it leads to things like differential equations, which are one of the, probably the most applied, the most applicable and used parts of mathematics. If you point at any object around you, there's going to be tons of calculus that went into the making of it, from the electricity that was used to make it, to the tools that were used to make it, to the design, to the way it was shipped around the world. It's in everything that's around us.
So infinity is all around us, but it still makes my head spin and yearn for those simple days when the highest number conceivable was
7.
But why is that new film called Infinity War? Maybe it's a nod to the 2 hour and 40-minute runtime. That was Eugenia Cheng, author of the book Beyond Infinity.
We're all familiar with fingerprint scanning or voice recognition to unlock phones. But imagine having a mini laser built onto a contact lens to confirm your identity. Scientists from the University of St Andrews have created ultra-thin lasers from flexible materials that can stick onto banknotes and contact lenses and be used as wearable security tags. Izzy Clark spoke to Malte Garter to find out more.
A laser is a device that produces a very special type of light. It generally comprises of 3 main components. The most important component is a so-called gain medium, which is a material that can literally photocopy the particles of which light is made, the so-called photons. And then the second component is a resonator. That's a structure that confines the light within the gain medium for a long enough time for the photocopying process to work. And then the third component we need is a source of energy that drives the gain medium, that drives our photocopying machine so that the laser can operate. Our laser, like all lasers, comprises of these 3 components, but we've literally stripped it down. In particular, we have removed the rigid substrate, which is a structure onto which normally the laser is bound or confined. So we end up with just an ultra-thin film that's less than 1,000th of a millimeter thick, which contains the gain material and the resonator structure to confine the light.
So basically, this is an incredibly thin laser.
Yes, correct. Incredibly thin, approaching the ultimate weight limit of a laser.
So how do you make these?
So like all other lasers, we start by having a planar sheet of glass or silicon wafer, which we call the substrate, and then we produce our laser on top. But the trick here really is that we initially put down what we call a sacrificial layer, which is a layer of a material that can later on be dissolved away, so that then the laser that has been built on the substrate detaches from the substrate, and then we have our laser membrane, our sticker that we can put on other things.
In my mind, I'm sort of imagining like one of those just transfer tattoos.
It's a little bit like that, I guess. This is the first time someone mentioned this, but it's a little bit like that. I agree.
And so why would we need something like this?
So we have a number of applications in mind. Most importantly, because the laser is so thin and because it's mechanically flexible, we can now take the laser membrane and stick it onto a variety of different objects. And this then allows applications, for example, in authentication control, where we can use the laser to tell us whether an object is real or fake.
Okay, so like what?
So our lasers are extremely efficient in turning energy into laser light, which means they can produce laser light, but very low intensity laser light. So low that it's safe to produce it in your own eye. So one of the most important things, of course, to verify sometimes is the human being itself, is the person who they claim to be. We have put our lasers on contact lenses that a person can then wear, and essentially they then shoot a little laser beam out of their eye, very much like Superman does. But we don't use this as a weapon, but we really just use it as an authentication device.
So how does that authentication work? How is it that by looking at a little beam from one of these flexible lasers, that then gives enough information to say, okay, yes, this is the real deal, continue as you want?
So lasers emit light of a very specific color, or we also say of a very specific wavelength. And we can measure the wavelengths of the light that's being emitted. And in our membrane lasers, that becomes a unique feature of each laser or each set of laser devices that we make. And we can increase complexity a little bit here and combine several lasers on one contact lens, each of them having a slightly different wavelength. And then this becomes what we call a laser barcode or an optical barcode that really uniquely identifies one contact lens, one laser membrane, and then also the person wearing it.
Not sure I'd enjoy a laser in my eye, but real-world Superman laser vision could be fun. That was Malte Garter from St Andrews University, and that study was published in Nature Communications.
And if you'd like to find out more about those news stories, then head to our website, thenakedscientist.com. You'll find references for the papers, along with transcripts for each interview across every Naked Scientist show we've ever made.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
You're listening to The Naked Scientists with me, Georgia Mills, and Izzy Clark. Now in the next part of the programme, it's over to Izzy, who's dipping her toes into water.
In the next decade or so, half the world's population could be living in areas where there isn't enough water to go round. Here in the UK, 40% of our food is imported, a lot of it from areas of high water stress, leaving us vulnerable if the taps run dry. I'll be finding out where we get our water, what happens once it gets flushed away, and could we really run out? Turns out, our planet Earth is a rather watery place. Water's in the ground, it's in our atmosphere, and it covers 71% of the Earth's surface. Now, our water supply never stays still. It is constantly moving from place to place, and that's thanks to something called the water cycle. Jonathan Bridge is a physical geographer at Sheffield Hallam University who explained how it works.
It's essentially the movement of water from place to place on the Earth's surface. So it's easy to see that most of the water is in the oceans. The sun then adds energy to the surface of the ocean and evaporates water. So it's a sort of purifying process, if you like. What's held in the atmosphere is just the water molecules, and those salt molecules or those salt ions are kept within the sea. So gradually it became saltier over time. And then when the atmospheric conditions are right, that water vapour then condenses and forms droplets, which fall as rain or snow or other types of precipitation.
Something us Brits know all too well. Now, this heating and evaporating is all about transferring energy. It's like when your body becomes too hot, sweat evaporates off of your body and carries the excess heat with it into the air. And the same happens with the surface of the Earth. As water evaporates, heat is carried from the Earth's surface into the atmosphere, and likewise, as rain falls down, heat can be transferred from the atmosphere back to the ground. But how are these all-important clouds formed?
The atmosphere exists at various different temperatures and pressures, and the ability of gas to hold water vapour in its gaseous form depends on the local temperature. So as the air containing the water rises, it cools down and the water vapour loses its ability to exist in a gaseous form, and so it starts to condense out and turn into tiny droplets of liquid water. So that forms clouds, and then eventually those droplets of water grow sufficiently large that they can't be held up by the air anymore, and so they fall to Earth under gravity.
Essentially, the rain falls to the Earth's surface, and one of three things can happen.
If you've got a natural landscape with lots of vegetation there, trees and plants and so on, then quite a large fraction of that rainfall is caught by the plants, either directly by falling on their leaves and being absorbed, or it goes into the soil and then the roots immediately take that water back up. Maybe 40% of the rainfall is immediately recycled via the plants and ends up being returned to the atmosphere by a process called evapotranspiration. So that's part evaporation and part transpiration, which is the sort of plant breathing process, if you like to think of it like that.
Or option number 2.
If it's not caught by the plants, then it can infiltrate into the soil and into the underground, into the subsurface. So some of it will go into the soil and be transferred, and it can flow through the soil horizontally. Some of it flows vertically down into the deeper subsurface and eventually forms groundwater, which is held in porous rocks deep underground, and that is a long-term store. There's some groundwater aquifers, some reserves of groundwater which 30,000 years old, which are sort of almost fossils of water which fell a long, long time ago. Other aquifers are much more shallow, and their recharge rates or their turnover rates are more rapid. The final pathway is almost the most obvious one we think of when it rains, and that's flowing over the ground surface. So overland flow, which eventually runs into streams and rivers and lakes and forms the water we see on the land surface. And in natural conditions, that might only be 10% of the total rainfall.
And obviously, it's called the water cycle for a reason. This surface water runs into rivers, which combine to make bigger rivers, and the bigger rivers run down to the sea, collecting salts and rocks with them as they go, and the process starts all over again. But how does this water then get into our taps? It depends on where you're from. In Cambridge, we get 50% of our water supply from water stored in rocks. This is known as groundwater, which is relatively clean because it's naturally filtered as it travels under the Earth's surface. And the other 50% comes from surface water sources, like reservoirs. Not all places have such an even split, but it helps to have multiple options in case there's an unexpected turn in the weather, which could affect supplies. Now, local suppliers, like Anglian Water, pipe over 1 billion litres of water a day to houses in the area. To put that into perspective, that's enough piping to go from the UK to Sydney and back. It got me thinking, how much of my day actually relies on clean water? Well, there's my morning shower and the teeth cleaning ritual, so that's twice a day. Plus numerous trips to the bathroom, flushing and hand washing included. A few more hand washes before eating or handling food, and definitely at least 5 cups of tea, and maybe a few glasses of water on the side. And actually, we're in a very fortunate position. The water that comes out of our showers or garden hose is as clean as the water in our taps, going through various stages of filtration and chemical removal to make it safe to drink. But not everyone has that luxury.
Today, 844 million people are struggling to access clean water close to home, and 1 in 3 people don't have access to a decent toilet of their own. So as you can see, the situation's really quite stark.
That's Helen Hamilton. She's the Senior Policy Analyst for Health and Hygiene at WaterAid. So how can charities like WaterAid classify whether someone has access to water or not?
Statisticians all over the world now record where people get their water from, how far they travel, and the source that they obtain it from. So that means it might be boreholes or accessing it from groundwater. And in terms of measuring it, if the whole round trip, so going to collect your water, queuing up to get it, and then coming home, takes longer than a 30-minute round trip, we no longer count that as access.
So it's within this 30-minute journey to get water, come back, that's almost the limit.
That's very much the bare minimum, and we know that even that can have a huge impact on communities. We know that, it's mainly often up to women and girls to find and collect water. And, if we think about a woman who's collecting the UN recommended amount of water, so that's 50 litres per person for a family of 4 every day, and they're having to go to a water source that's a 30-minute round trip from their home. Even then, we're talking about a woman spending 2.5 months a year alone on this one task. And we know that having clean water, access to decent sanitation and good hygiene is possible for everyone, everywhere by 2030. And we know progress is possible because if we look at examples like India, we've seen that within 15 years, 300 million people have got access to clean water.
So, why are we putting in all of this effort to make sure we have clean water? Why is it so important?
So it's essential to have these 3 elements of access to clean water, decent sanitation, which means access to a good toilet, and every single day to practice healthy behaviours, which means washing hands after you go to the toilet or before you prepare and eat food, and having clean food storage. And bringing all these things together is the best way to ensure that people are much healthier and have a better quality of living.
Because I imagine that that last one, the good hygiene practices, basically underpins the values of the first 2, essentially.
It does, and we know that often changing behaviours is very hard to do. If you ever think about when you've tried to pick up a New Year's resolution, actually, the thing that you're doing isn't always hard, but changing that behaviour and then you're incorporating it into your day-to-day routine can be quite a challenge if you don't really think about how you're going to do it. So making sure that good hygiene and the sort of hand washing and thinking through how we can be healthier is part of people's day-to-day life is absolutely critical for protecting yourself against these diseases and having a better quality of life.
And so what are the problems and what are the health risks because of not having access to clean water?
At the moment, we're actually in a crisis point. This risks families' health. It stops families and communities from reaching their full potential. And, we know that diseases like diarrhea, cholera, pneumonia, conditions such as undernutrition, and even some diseases that you might never have heard of, such as blinding trachoma, all have links to lack of access to clean drinking water, lack of access to decent toilets, and a lack of good hygiene practices to keep people healthy. But also, we know that where people are going to healthcare facilities, if you think about when you go to the doctor, you rarely do that because you're feeling well. You always go because you're feeling poorly. And so where people are going to healthcare facilities to try and see a doctor, and there's 38% of these healthcare facilities don't have access to clean water, this means that doctors and nurses who are either delivering babies or treating patients for critical illnesses, they're not able to wash their hands or sterilise implements properly. We know that more babies survive when hospital staff are not only trained in these medical techniques, but also given, resources and training so that they can really put in place good infection prevention control procedures. And fewer children fall ill with diarrhea when communities receive clean water points and good latrine and hygiene promotion. So a significant amount of disease can be prevented through access to this safe water supply, adequate sanitation, and better hygiene practices. And we even know that 1 in 4 newborn deaths are due to infections and sepsis that might have been prevented if babies had been delivered in places with safe water, decent sanitation and hygiene.
And are there any ways that we can sort of improve that? What do WaterAid do to sort of help move that along and make sure people do have this access to clean water?
Organisations like WaterAid work with communities and understand what the challenge is, and then work with them to build up the provision of services with them and their governments. And this means that the services need to be fit for purpose, they need to be built to last, and this means involving the people who are going to use those services in making decisions about what they should be, where they should be, from the very start, and also making sure in this day and age that they're equipped to withstand future environmental challenges, such as climate change. So that might mean having wells, boreholes, accessing groundwater where that makes sense, or rainwater harvesting. It's often a complex mix, and understanding what's right for that situation.
And every situation across the world is different when it comes to water supply and treatment. Here in the UK, there's a rather lengthy process between turning on our taps and flushing the toilet. Long story short, water is taken from nearby rivers or groundwater, thoroughly cleaned and sent to our taps. Once we're done, we send our wastewater down the drain to be treated before it's released into the environment, and the process starts all over again. I met with Reagan Harris at Anglian Water's sewage treatment site to see it for myself. First up, the gravity sewer. Basically, an 18-metre drop above all of Cambridge City's sewage.
It's a long way down. Oh, that's a stinky. That's a smell.
So from here, the sewage is pumped to essentially the first part of the treatment process, and that is basically where we start to filter out all the solid stuff, all the rags and unflushable things that people put down the drain. So we're talking about things like wet wipes, sanitary products, cotton buds, and they're the things that Anglian Water always ask people not to put down the drain, but unfortunately we still get a fair few of them that we need to take out first before we go on to clean the water any further. So, within our region alone, we're looking at kind of 800 tonnes of unflushables per day that we take out of used water. That's why we're always asking people to only put the 3 Ps down the loo. So that's pee, poo and toilet paper. And it basically, it's something that we need to try and avoid if we can.
And so what happens to these unflushables that still make their way into this system?
Well, ultimately they're screened out here initially, and then they do end up in landfill because there's nothing else we can do with them. They can't be recycled, they can't be composted. Essentially they are collected here, they're screened off the water, and then they end up going to landfill, which is why, again, it's really important that people don't do it.
Should we go and take a look at the next step? So it's like a conveyor belt of basically wipes, nappies and other things, really.
That's it, exactly. These are the screens that essentially take out all the solid matter from the used water that comes to us. So it's a vital part of the process, really. This is the initial part of the water recycling process.
So that's the big unflashables out of the way. It was then onto the second part of the screening process. And the water was still looking rather murky at this point.
The next stage is that we wash all the grit and the little bits and pieces out from the water, and they're collected below us. We get all the kind of runoff from the road, so you can imagine when water runs off the road, it goes down the drain. All that is kind of contains grit and lots of other, little stones and particles. They all get washed and separated off here. Interestingly, we also get the lovely little bits of sweet corn and things like that, and also medication and stuff that people have flushed down the loo. So all that kind of slightly bigger, granular stuff is collected here.
Oh God! Oh my gosh! There is so much sweet corn in that skip.
He's not.
I really wasn't expecting to see that.
Once I'd recovered from the sheer amounts of sweet corn that gets filtered off, we skimmed past 5 massive concrete cylinders, otherwise known as primary settlement tanks. Here, the big solids in water settle to the bottom of the tank and are sucked away to be used as fertiliser for agriculture. And then we arrived at our 4th destination.
These are what we call our sludge activation treatment part of the process, essentially. And what they are is 4 lanes of water, of the used water. Each lane holds about 6 million litres. And what we do here is pump in dissolved oxygen to aerate the water. This allows different bacteria to grow, which actually eat the sewage and break it down. They're the same sorts of bacteria that we have inside our own guts. And what we do is essentially provide them with the perfect conditions to grow and multiply to help us break down the sewage. It's a completely natural process, and all we're doing here is allowing something that's natural to do its job and help us in the water treatment process.
So we can see these little whirlpools in front of us. Is that just the oxygen that's being pumped in to help these little bacteria that live in this water to munch down on whatever is still left floating around?
Exactly that. The oxygen that we pump into the water allows the bacteria to flourish. That means they can munch down on all the baddies that make sewage a pollutant, things like ammonia and phosphate as well. And you can see actually as the lane gets further and further away from us, the water actually gets stiller, and that's because as it moves along, the bugs are doing their job and essentially taking out the baddies that we need them to. So by the end, you'll see that the water is actually much cleaner and actually isn't that different from what you'd see in your local river or stream.
Because in front of us we've got a big algae, it's almost like an algae pond really, lots of movement, and then yeah, you're absolutely right, as it goes further on there's not as much action.
No, not exactly, and that's because we're nearly at the end of the treatment process now and the water's nearly ready to go back to the river.
So we're now finally at the final stage of our water treatment. So has there been solids in the water up until this very final stage?
Yes, solids of varying degrees of sizes. So we saw the big solids removed right at the beginning, and then gradually as the process goes on we get smaller and smaller and smaller until we're here at our radial flow tanks, and this is the final stage before the water is returned to the river. And essentially what happens here is the water is allowed to settle here, and then it overtops this little weir in front of us, and you can see the water's really, really clean at this point, and it just traps any remaining solids in the water, and they're taken away and treated at the sludge treatment process.
So this is pretty much the cleanest water we will see before it goes into a river, really?
This is it. This is exactly how it goes back to the river, and you'll find that the water that comes off of this treatment works is as clean, if not a little bit cleaner than what's actually in the river already. We have tough environmental standards we have to comply by before we put water back into the environment, and we're absolutely committed to doing that, and we're regulated by the Environment Agency on it. And this is it. This is the final stage.
But not drinking water, though?
No, I don't think you want to drink it, just as you wouldn't want to have a glass of water out of your local river. But it's definitely clean enough for the ducks and the fishes and any wildlife that's flourishing in the River Cam nearby.
And so why is it important to take our sewage and treat it in this way that we've explored?
Well, it's really important that we're able to return water to the environment. Our role at Anglian Water is to balance the needs of our customers, so in terms of allowing people and businesses to have the water they need to do day-to-day washing, using their toilets, all of that stuff, as well as supporting local business and the economy. But we can't do that at the expense of the environment. So what we have to do is treat the water that we use to a really high standard and then give it back, because there is only a finite amount in the world that we can use.
And whilst this process is thorough, it's also expensive. What if we could reuse some of our wastewater without this huge amount of treatment? Like the water we've used for our morning shower or our washing up, otherwise known as grey water. Back to Jonathan.
The sewage treatment process is able to be recreated quite nicely in natural reed bed by constructing a wetland environment where you allow your wastewater to pass over some gravelly sandy zone and then settle out in a reed bed. You actually are mimicking the exact processes which are used in an industrial scale. But in principle, you could take the water that's come through your reed bed filtration system and put it back into your washing machine, into your washing up water, into these other uses which don't require that very high standard.
And I imagine another challenge is the fact that, say, this reed filtration system in a big city, say like Cambridge or London or elsewhere, that would probably be quite hard to handle.
It takes up potentially a lot of area, yeah. When we're living cheek by jowl in high density urban environments or in apartment blocks and that sort of thing, there simply isn't the space to have that traditional extensive filtration system.
Is there any way around that though?
Well, yeah, people have been designing sort of green infrastructure, so green buildings which do incorporate these facilities. So you may have seen buildings with green walls where you have plants planted all the way up the side of a building. Now, that can be for several different purposes. It also has a cooling effect, and so it can be used for the building's energy usage. But there are systems which have been essentially designed to do that same treatment train that we saw in the reed bed filtration system, but sort of vertically. So you pump the grey water in at the top and it trickles down through the green wall, being treated by these natural plant and microbial systems as it goes. And so at the bottom of the wall, you would come out with that water that you can either treat or directly recycle. So the technology and the ideas are there, and people have designed entire skyscrapers built around this sort of technology, which also incorporates food production and self-sufficiency on a large scale.
So why aren't we all doing this? It sounds amazing.
So a problem with these vertical systems is what would happen if it went wrong. Effectively, because they're prototype, because they're new technologies, we're not sure what their limits and constraints are to things like overflow from a very heavy rainstorm or something else going wrong. And the problem there is that the building which relies on that treatment suddenly doesn't have a water supply for that type of water anymore. So it's potentially less robust or less guaranteed supply than our existing centralised water supply systems.
So there's still a way to go, but for places like Cape Town in South Africa, a solution like this would be a saving grace. 98% of Cape Town's water comes from dams, but with 3 years of low rainfall, they're using water more than it's being replenished. The city is running out. Georgia Mills spoke to Kevin Winter from Cape Town University, who is all too familiar with the prospect of the taps turning off.
Day zero is a date when the city would effectively run out of water, and the water in our dams, when it got to a level of 13.5%, that's the point at which taps were being turned off right across the city. And about 75% of the city's residential area, some businesses, even institutions and so on, would find their water cut off, and individuals would then have to go queue up in 200 different places scattered across the city and collect their rations of 25 litres of water for each day.
Since this has been announced, the date of Day Zero has changed. So what's been happening since that?
Was forecast to be the 9th of April. And then a number of factors came into play to enable us to essentially avert Day Zero. And there are three big things. The first, that citizens have reduced their water demand dramatically. In January 2016, we were on average using about 235 litres per person per day, and we're now currently using about 70 litres per person per day and hoping to continue to get to 50 litres per person per day. And no other city seems to have recorded such a dramatic change in water use. The The second major one is that farmers have had their allocation of water terminated, and so they no longer take in water from the same dams. And then last of all, we've had some rain, which has cooled down the weather to some extent. It hasn't made a great deal of difference to the volume of water stored in our dams, but it has reduced the evapotranspiration, the loss of water from those dams.
Right, and so now the day is now further away, but it's still sort of looming over the city. So what will happen when that day arrives?
When taps are turned off, the impacts are going to be large. Unless they've found alternative sources in the interim, it's unlikely that we'd be able to keep schools, large government buildings and so on running if they are dependent entirely on potable water from the city supplies. An unworkable arrangement in which citizens queue up to go and find water in these various stations across the city. You've got to get there, first of all. You've got to spend time queuing up for that water. And you've got to take that water somehow, which is heavy. 25 litres is substantial. And you've got to take it back to your home. And in the meantime, we get on with these new projects that will be able to supplement our water supply so that we can survive what is an absolute terror, a catastrophe in lots of ways.
You mentioned there are other projects. Are people looking into this then, other forms of water supply?
Yes, indeed. And the new projects are threefold. The first one is to draw more water from our aquifers, and that is a project ongoing at the moment. We'll see what the yields are like, and there are loads of issues around drawing water from an aquifer and what kind of damage you can do to an aquifer. And the second one is to reuse that water, and there are projects trying to upscale the amount of reuse that's taking place across the city. And then we have a number of very small-scale desalination projects that are being undertaken at the moment. They are still at their infancy, and at this point, the city and the national government envisage only fairly small-scale projects, and at some point later, they might be ratcheted up to meet a higher demand.
And are people taking matters into their own hands at all? Are we seeing changes in behaviour other than just sort of using less water?
Yeah, people have gone and sunk private boreholes in and around their properties, and in many cases used that as a sustainable argument that we now no longer draw in water from the dams and the storage systems. We are drawing it from the ground, and that's our right, and we can take as much water out as we like, and no one's really watching us.
But presumably that's not an infinite resource.
Well, it's like putting a straw into a glass, isn't it? And if you draw the short straw, you're going to find it's not yielding any water. Those who can afford go down deeper, and of course it does have implications. And when you go down well below the water table and start to draw from that, and because we're a coastal city, there's every chance that you'll start to draw seawater into that groundwater, and then becomes a real danger and a moment in which aquifers, which are currently yielding very high qualities of fresh water, can be contaminated, and it takes a long time to undo the damage.
Right. And Cape Town has always been in the same part of the world, obviously. Why is this happening now?
Yeah, that's a really great question, because in the past, what we normally would see during the winter rainfall period is that every 3 to 5 days, a cold front system would arrive into our region and pass over the Southern Cape and fill our dams. And we relied on that, and a very different rainfall is now evident in what we see now. The high-pressure systems called the South Atlantic High are dominant, and that dominant system, high-pressure system, is forcing these cyclones to travel southwards. So we can see them. They're really intense on the satellite images, and we get so disappointed because they migrate off southwards. It could be through the warming of the oceans that are beginning to affect the dominance of that system. You could look at global warming, you could talk about climate change, you could talk about disturbances in the upper atmosphere. They're all in the mix and could well be factors that need to be understood if we are going to understand now why our mid-latitude cyclones are just missing us.
And do we think this problem is just localised to Cape Town, or are we going to see more of this happen in other places?
I think the big warning is that if you are reliant on a source of water, in our case 98%, as I said earlier on, and you're having weather variability like this, whether it is even over a short period of 5 years, and we've watched California and Arizona and Australia and cities within them have experienced much longer periods of drought, 10 years drought or more. And if you're only relying on a source of water, you are going to need to look at these warning signs a lot more carefully. The one thing that I think we've learned is that in 2014, we experienced some of our best rainfalls. And by the end of 2014, it looked like that our dams were full. There actually was no real need to get scared about what the future holds here. And then suddenly, by the end of 2015, the picture started to look very different, and it has continued to do so over the next 2 years. In other words, it's extremely quick. And if this is the signs of climate change, well, it's rapid. Those are the signs you've got to start looking for. And if you start to see that happening, you need to start looking at a diversification of water supplies.
Fingers crossed some rain comes their way. That was Kevin Winter from Cape Town University, and thank you to all our other guests this week, Jonathan Bridge, Helen Hamilton and Reagan Harris. That's it for this week on The Naked Scientist, but we'd like to leave you with this. Cape Town can be a warning for all of us to pay attention to the amount of water that we use. According to Cambridge Water, the average person in the UK uses 150 litres per day. That's about 6 to 9 litres per toilet flush, 45 litres for a 5-minute shower, and 50 to 100 litres for a full load in the washing machine. Kevin's advice for anyone around the world is to start noticing how much water you get through on a daily basis and work out where to cut down. Perhaps it's putting tissues in the bin rather than the toilet bowl, or not letting the tap run for too long. You can't manage what you don't measure. Do join us next time, where we'll be putting your weird and wonderful questions to our panel of scientists for a Q&A special. And if there's something you want to ask, then do send us an email. That's chris@thenakedscientist.com. The Naked Scientist comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. I'm Izzy Clark, and thank you for listening. Goodbye.